Alright, so the next question is problem number 3283, which is marked as a Leetcode hard problem, and the title is maximum number of moves to kill all pawns. So there's a 50 cross 50 chessboard with one knight and some pawns on it. You're given two integers kx and ky, where kx, ky denotes the position of the knight, and a 2D array positions, where positions of I is equal to xi, yi, which denotes the position of the pawns on the chessboard. Now, Alice and Bob play a turn-based game where Alice goes first. In each player's turn, the player selects a pawn that still exists on the board and captures it with the knight in the fewest possible moves. Note that the player can select any pawn. It might not be one that can be captured in the least number of moves. In the process of capturing the selected pawn, the knight may pass other pawns without capturing them. Only the selected pawn can be captured in this turn. Alice is trying to maximize the sum of the number of moves made by both players until there are no more pawns on the board, whereas Bob tries to minimize them. Return the maximum total number of moves made during the game that Alice can achieve, assuming both players play optimally. So Alice is trying to maximize the sum of the number of moves made by both players until there are no more pawns on the board, whereas Bob tries to minimize the sum. Okay, so that's the problem. Note that in one move, the chess knight has 8 possible positions it can move to, as illustrated below. Each move is 2 cells in a cardinal direction, then 1 cell in orthogonal direction. Okay, so this is the example. So basically, a knight, as you know, in chess, it moves 2 steps in one direction and then 1 in the opposite. Not the opposite, 2 steps in a cardinal direction and 1 in the orthogonal direction. So basically, perpendicular to that, it moves. So let me show you. First move, if you see, these are the two cardinal direction moves and then 1 orthogonal one. Similarly, this one, 2 cardinal moves, then 1 orthogonal direction move. Similarly here and here as well. And these are basically all the moves that the knight can take. So there are 8 possible moves that it takes, right? Now moving on to the first example. So kx is equal to 1, ky is equal to 1, position we start from 0, 0. Right, so this is the animation. You can see that the knight starts from kx 1 and ky equal to 1. So kx is equal to 1 and ky is equal to 1 is this position, right? So this is the starting position, as you see. So it starts from here, then it takes the move it comes to this point, then it takes another move like from here to here, then from here, basically this is the first move, this is the second move. Now from here to it moves here, this is the third move, and finally it takes the fourth move and reaches the pawn and kills the pawn. So basically there were 4 moves required. So you can see the animation. First it goes from 1, 1 to this point, and then to this point, then here, and finally back to 0, 0. So this is our first example. Now second example, you can see we start from 0, 2. So this is the point we start from, and the positions, it basically starts killing all the pawns in this fashion, right? So you can see that it started from here, moved here, killed this pawn first, moved here, then killed this pawn, then moved here, then here, then came here, and finally killed this one. So these are the pawn locations. Alice picks the pawn at 2, 2 and captures it in 2 moves. Then Bob picks the pawn at 3, 3 and captures it in 2 moves. Alice, now since we are alternating between Alice and Bob, Alice picks the next one and captures it in 4 moves, as you can see here. Right, and finally we have this example. So basically, let me get to the approach now. So we are going to be, in order to traverse the chessboard, we're going to be using BFS, or we can also use DFS, no problem in that, and with mask and DP as well. So this is essentially a DFS or backtracking problem. Each time, the knight can choose one of 8 moves and proceeds if it stays on the board. If a pawn is at the position and it's not captured yet, it counts as 1 move. That is, it is captured, right? We try all possible sequences of captures using recursion and memoization to avoid recalculating some states. Now, the step-by-step approach. So firstly, we set up the board, store pawn positions in a set for over 1 lookup, then use DFS to try all 8 knight moves recursively, then track the captured pawns in a visited set or with a bit mask, memorize the state using current knight coordinates and set of visited pawns to avoid recomputation, and return the maximum number of pawns captured across all valid paths. So this is basically our approach that we use. So firstly, we use BFS to pre-compute the knight distances. So we use BFS from every position, that is knight plus pawns, to every other position to compute the minimum knight moves. So for n pawns plus 1 knight, we have n plus 1 BFS traversals, and for each movement, we fill the 2D distance table. Min distance I, j is the minimum moves taken from going from position of I to position of j. So position is actually this vector, right? Position of I to position of j, and we will also basically append the prepend the knight's coordinates here in the starting. So position of I, j basically means that from any one particular position to any other one, I to j, right? So we are basically going to be filling it in the minimum distance I, j 2D vector, right? And then we have minimum max with memoization with mask GP. So at each game state defined by index, mask, and turn. Index is basically knight's current position index in the position vector. Mask is a bit mask of unvisited pawns, and turn is Alice or Bob. So basically, this is the flag that will keep alternating between Alice or Bob. So we simulate Alice's turn to maximize the total moves and Bob's turn to minimize total moves, and we memorize each state to avoid recomputation. Now let us go over the complexity. So BFS for each of the n+1 nodes, that is one knight and n pawns. So that is O of n times 50 times 50, O of n times 2500, which is a constant 2500. So O of n is for the BFS. And DP states DP index mask, where index belongs to 0 to n and mask belongs to 0 to the power 0 to 2 to the power n. Right. So we have these all these cases. The total DP states are basically n times 2 to the power n, n times 2 to the power n. And each DP state tries up to n pawn positions. That is n times this value. So the total complexity would be O of n square times 2 to the power n times n times 2 to the power n plus for the BFS n times 2500. Right. So that's the time complexity. And space complexity, we're basically taking a 2D vector, minimum distance, O of n square, and dp of this. So this means 2 to the power 15. This notation actually means 2 to the power 15. Right. So maximum 15 pawns since we can have. We have this as state. Right. And this is the space complexity. Now let us get to the most important part, that is the coding part. So basically, I have summarized here what we are going to do. So knight moves, we are basically using BFS to compute shortest path between knights and pawns. Then BFS to find shortest path between positions using knights allowed moves. Then we are using bit masking to represent subsets of unvisited pawns up to 15. So 2 to the power 15 is basically these many masks. Then minimax DP recursively simulate Alice Bob moves with optimal scoring, and memorization to save intermediate results for each index comma mask pair, because we are avoiding recalculation of subproblems, right? So that is about the concepts and their uses. Now let us get to the coding part. So basically, firstly, I have defined all 8 possible moves for a knight. So basically, this means that let's start with the first one. This means that in the x direction we are adding 2, and for y we are adding 1. So if you have a grid here, let me say this is the grid that we have, right? So this is x. X is basically the denoting the row, and y is the column. So when you do x plus 2, that means let us say we are here. So x plus 2 would be, this is x plus 1, and this becomes x plus 2, right? So we are moving 2 down, and y plus 1 actually means 1 column to the right. So basically we are here, right? So x plus 2, y plus 1 means that 2 down and 1 right. Similarly, 2 down, 1 left is 2 comma minus 1, and you can see all of these are mentioned, right? So I have coded this up to show you how the combinations of 2 and 1 can work. So you have plus minus here and plus minus, so 4 combinations of this, where we are actually moving. So let me just draw it for you yourself. 2 down, 1 right actually means 2 down, 1 right. This is the movement. Then you have 2 down, 1 left, so 2 down, 1 left. Then you have 2 up, 1 right, 2 up, 1 right. Then you have 2 up, 1 left, right. This is another movement. Now you're basically going to be moving 1 down and 2 right, so 2 right and 1 down. Then 2 left and 1 down. Then 2 right and 1 up, and 2 left and 1 up. So basically all the 8 possible knight moves are covered with this, with the help of this directions vector or vector. Now isValid function returns whether the cell that we are at is in bounds or not, right? So I greater than equal to 0 and I less than m, which is the number of rows, and j greater than equal to 0 and j less than n, which is the number of columns. Now we use BFS to compute minimum number of knight moves from x comma y to all other pawn positions in the position array, and results stored in minimum distance of index comma I. So we are passing x comma y and the index and minimum distance 2D vector, and the position 2D vector, right? So we made a 2D array for distances from x comma y labeled as t, and q, in this we'll be storing the I and j coordinates, right? So q is basically storing the I and j coordinates, and we first initially push the x comma y that we are currently at, and distance to itself is 0, so we push t of xy is equal to 0. Now we start up standard BFS traversal. While the q is not empty, we extract the I and j coordinates from q's front and pop it out, and we're going over all the 8 directions to get to the neighboring locations. So the graph that I showed, the picture that I showed you, basically this is basically the point x comma y starting from this point, and all these other locations, these ones, like all of these are the possible neighbors that we can go to from x comma y in one move. So these are the nx comma ny. So that is denoted here, nx comma ny, right? And now here we check if the cell that we are going to is inbounds and has not yet been visited. So if is valid, nx ny, and 50 cross 50 is the matrix size, and it has not yet been visited. So t actually marks the visited. So if it is not yet been initialized, so that would mean that it is still -1. So then we update this visited, that is one move from the current cell, 1 plus t of I comma j, and push it into the queue. and once we come out of this while loop, we fill the minimum distance with the distance from night at index to all other positions. So for int I is equal to 0, I less than position dot size I plus plus. Int row is equal to position of I comma 0, and column is equal to position of I comma 1. Right? And we store the minimum moves from x comma y to position of I in this 2D vector minimum distance of index comma I. So at this particular cell, index comma I cell, we store the key of row comma column. Now we're moving on to the solve vector, right? So it basically recursively simulates all paths with minimum max strategy, where index is the current position index, that is the night's location. Mask is the bit mask of remaining pawns, 1 if still present, and n is basically the total number of positions, 1 9 plus n pawns. And Alice is basically the flag that we use, that is true if it is Alice's turn, or if Alice is false, it means it is Bob's turn. So this keeps alternating the flag between Alice and Bob. And dp plus bit mask to solve for maximum total moves from index with mask of remaining pawns. So this is the mask that we use, right? dp of mask and bool Alice, the flag. This is the mask index and the minimum distance 2D vector, and n, the number of total number of positions. So firstly, we have the base case, that is all pawns have been taken. So if mask is 0, we return 0, that is no more steps or moves are required. And next we have, if since we are using memoization, if dp of index comma mask is not equal to -1, we return it. That is, it has already been computed, so we don't want to recompute it since we have overlapping subproblems, right? And result we have declared, right? We'll be storing our answer in that. So if Alice is true, that means it is Alice's turn. So we set result is equal to -1 because we have to maximize it. So we set a small number, right? And for Bob's move, we have to minimize it. So we set a very large number, that is 189 for Bob's move. Now we try all the remaining pawns, right? So for I is equal to 1 to n, since the knight is actually in the position vector, we have stored the knight's coordinates at the 0th index, right? So we are starting from 1 and going till n. So all the remaining pawns, if mask exists, and basically 2 to the power I minus 1 is this value, 1 to the 1 and this arrow to the power I minus 1, so 2 to the power I minus 1. So if this is the condition that is being met, moves is equal to minimum distance index from I, and if Alice is true, so we have to maximize it. Result, comma moves plus, we are adding the moves that we are taking from this, plus the recursive call, solve minimum distance I and mask to the power 1 I minus 1. So this actually means mask to the power of this value, that is 2 to the power I minus 1. Right, so these are the number of combinations that we can have. N and not Alice, because now we have to alternate it between Alice and Bob. So not of Alice we pass, as the boolean flag would be changed. And similarly for Bob we have to minimize it. So this is the same. This remains the same, just the max changes to minimum since we want to minimize Bob. And finally we stored our result into the dp of index comma mask. Right, and now we have the maximum moves function. So n is equal to position dot size. Position vector is basically going to store knight plus all pawns. So in the position vector, we store all positions of pawns as well as the knight starting coordinates. So we push back the starting coordinates of all the positions, and as well as that the knight starting position, right? So firstly we have the knight starting position and then all the other pawns positions. And minimum distance of I comma j is basically minimum knight moves from position I to position j. So vector of vector of n type minimum distance we have declared. So this is of size n plus 1 cross n plus 1, and we have initialized all the values with 0. So this is basically going to store the minimum distance moves from position I to position j, right? And this is basically what we are doing, right? So now we traverse for basically all the positions that we have, since we have n plus 1 calls for BFS, since we are going for the knight as well as all the n pawns. So we will get the x and y coordinates from the positions 2D vector and call BFS for each of these x, y coordinates, passing I as the index and minimum distance vector we are passing, and position is the vector of in type in which we have stored all the positions. Then we finally call solve, that is knight is at the 0th index in position array, all pawns present, bit mask with all n bits set. So all n bits should be set initially, that is 2 to the power n minus 1, or it could be denoted by 1 left shift, 1 right shift, n minus 1. Bool Alice is equal to true, start recursion simulation with Alice's turn, and dp we have initialized 51 to the power 51, dp of 51 and 2 to the power 15. So basically 51 is the number of rows and 2 to the power 51 number of columns, and mem set dp minus 1 size of dp, right, for memoization, and we return a solve function. We're starting the index from 0, that is the knight's position, and going up to position dot size, all in bits set to 1, right, and Alice and dp we have passed, and yeah, that's it about the problem.